Okay, yeah, it's about 3:03. So welcome everyone. So I gather you had interesting discussion yesterday on the homework and any any questions on the dualities that we've been discussing uh, the past couple of lectures. Okay, so in today's lecture, I want to introduce some newer dualities which are relatively recent, at least in their complete form. They were not understood until about, I think, 4 or 5 years ago, uh, and uh, um, and they've had a significant impact in understanding, uh, various fractional quantum Hall states and various exotic spin liquid states. I won't be able to go into any of that, but I just wanted to introduce these dualities. Uh, the basic boson fermion duality is actually a bit old. There was a paper by Chen, Fisher, and Wu some time ago, which I've cited, which had the basic result, but it's been cleaned up much since then. And one of the reasons for presenting this, as you'll see, with the benefit of hindsight, these are actually very simple dualities, which follow directly from all the tricks we've learned so far in this course. So, and the main trick we have learned is if you want to describe some strongly correlated system, you take your basic underlying particle and you fractionalize it. And if you fractionalize into fermions, those fermions will occupy some bands. And then you give those bands some Chern numbers. And by just playing around with the Chern numbers that the fermions acquire, you can really build up a tremendous library of exotic phases. Basically, that's the trick we've been using over and over again for every exotic phase that we have uh, uh, discovered. But now we're going to apply the same idea, but to quantum phase transitions. We're going to look in the vicinity of some quantum phase transition and obtain a duality. In fact, the dualities we've already described, the Dasgupta-Hapton duality, can also be obtained in this way. And the basic idea is if you identify some simple quantum phase transition, and then you find two different ways to describe it. In one way, you take, say, the bare particles and you describe it using that. And another way, you fractionalize the particles and you describe it using that. As long as you're describing the transition between the same two phases, or the two sides of the transition are essentially the same, have all the same characteristics, and then you expect universality. You expect the universal description near the critical point to be unique. So then if you have two different descriptions of this universal behavior, it seems very reasonable to assume that those theories are actually equivalent. So this is a powerful tool for at least deriving, if not proving, equivalences between strongly interacting quantum field theories. So we are going to look at quantum field theories which do not have any exact solutions. The best we can do is to numerically study them or study them in some expansion. The trouble with the expansion methods is that these dualities we're going to describe don't hold except for the particular value of 3 space dimensions with certain number of components of the fields. You can't do 1/n expansion or epsilon expansion or anything because at every order in the expansion, the duality is not valid. It's only valid right at the particular point we're looking at. So in effect, these statements I'm going to make really should be considered as conjectures. There's no proof that these dualities exist, are actually true. But I think there's so much evidence for them, and also some numerical support that we do believe they're valid. The only proofs of such dualities come from supersymmetric generalizations. If you generalize this to supersymmetric ones, then there are stronger arguments, essentially proofs of analogous duality in supersymmetric theories. Okay, so that's the kind of a general flavor of what I want to talk about today. So I'm going to start with actually the simplest possible phase transition, which we've already met in the very beginning of the course, essentially, and that's the superfluid insulator transition. So we did the boson-Hubbard model, and we found that the boson-Hubbard model at integer filling had a trivial mod insulator phase, which is just the bosons trapped one per each site, and a superfluid phase. And this phase transition was described by the XY model, which was then described by the Seifert field theory that we've discussed even last time in the Dasgupta-Halpern duality. So we're going to look at precisely the same theory again, and writing it down, and we'll write it down not as in terms of a dual theory of vortices, which is what the Dasgupta-Halpern mapping was, but as a dual theory of fermions, the theory of fermions, which will describe the same model. So how do we do this? Well, as I've already indicated, the trick is fractalization. But let's first, let me set up the boson model. I'm going to take a little twist on the usual boson model. I'm not going to put one boson on every site. I'm going to put one boson on every other site. Now you might say, okay, then you're not going to get a trivial mod insulator if you have bosons that are filling. That's what we've learned many, many times in this course. But what I'm going to do is something you actually looked at a homework problem on several weeks ago. I'll take a lattice in which the sites are not equivalent. So there's the A site and then there's the B sites. So we call these the B sites here. And these B sites have on-site potential energy, which I called here epsilon naught. So here on the B sites, there's a potential energy of plus epsilon naught. And on the A sites, just to make it symmetric, there's an energy of minus epsilon naught. So when epsilon naught is large, the bosons will, of course, want to sit on the A sites. So these are the A sites here. These are the B sites. All the bosons will sit on the A sites. And if your density is 1/2 in respect to the original square lattice, then the ground state will be very simple. It'll just be one boson on every A site. There'll be boson here, boson there, and that's a unique mod insulator. There's only one such state if your density is exactly 1/2. Okay, so that's the mod insulator when epsilon naught is very large. And then as you turn down the interaction U, the boson will start hopping and become a superfluid. So what you showed in the homework, so here's the model again. These are bosons B with some hopping, nearest neighbor hopping, some on-site repulsion, and this eta I is +1 on sublattice A and -1 on sublattice B. And that's the epsilon naught. So there's a phase transition, and on very general grounds, and this is something you discussed, I think looked at in the homework, actually, you don't even need epsilon naught to be very large, as long as epsilon naught is non-zero. As any non-zero value, you're really at integer filling with respect to the new unit cell. The unit cell is a checkerboard lattice whose lattice, which is just a square lattice itself, but the lattice spacing is square root of 2 larger. So you have a new lattice here, which is connecting these points. So on that lattice, the filling is exactly 1 per site, and therefore you get, and that's the true symmetry, and therefore you get a trivial superfluid insulator transition, a conventional superfluid insulator transition. So what you showed in the homework was then, yes, this thing is described by, now I'm calling it phi, because we're going to use psi for fermions in this chapter. So this is our theory. So we have this theory here of a boson field phi, and that's a relativistic field theory. And as in previous duality considerations, it's useful to imagine that the bosons coupled to some external gauge field, A mu, with charge 1. So you just put a coupling, minimal coupling to the external gauge field. And so your partition function is some functional of A mu. So as you vary S, you go from the superfluid to the insulator, you will essentially become at the fixed point, Wilson-Fisher fixed point value. And so this is some functional of A mu and the distance from the critical point. So we're going to claim, as in the Dasgupta-Halpern duality, that I have another way of writing down this functional, which will give me exactly the same functional after appropriate mapping of this parameter S to the new theory. Okay, so that's one side of the duality. That's our boson theory. So we were interested in the boson theory where you're close to the superfluid insulator transition and as you tune S, you go from one side from the insulator to the superfluid, and you're just looking at the universal long wavelength properties of this strongly interacting field theory. Okay, this is the field theory that was first understood by Wilson and Fisher, and for which Wilson won the Nobel Prize because this was one of the first applications of the renormalization group. Okay. All right, so now we're going to write this theory in a completely different way. So what's the basic trick? The trick is the trick we've been employing over and over again. We're going to take our boson and write it in terms of two fermions. We're going to split it into two fermionic partons, which are called F1 and F. Okay, and then these partons will start hopping around on the same lattice. So the partons will also be at half filling or integer filling per the unit cell. So the F particles now will also hop on the same lattice. You'll have F particles sitting around here, and they'll go from hop around in the same some lattice with some Tij. So, if you want to do an honest job of this, you have to take this parton decomposition, put it into this original Hamiltonian. Now you get some 4 Fermi terms, and then you factorize them, and you find some mean field theory, and then you hope that the mean field theory gets the properties. In this case, we already know the properties, so this is, we're just creating work for ourselves. We understand this theory very well. We're just trying to write it out in a complicated way. Anyway, so you do that, and then you get some bands for these two partons. And we hope that that theory of these partons reproduces the properties of the superfluid and also of the insulator. Okay, so initially when it sounds crazy. How can you get how can I take fermions and get a superfluid? Okay, I can imagine getting an insulator out of fermions, but how to get a superfluid I have to condense a boson, and I'm not going to condense any boson. So how am I going to get a superfluid? Well, turns out you can. So what we're going to say is that we're going to take these two partons, F1 and F, and we're going to put them in some band by doing some complicated mean field theory. The only thing we know about the partons is that there's a density of them, which is 1 per unit cell of the bigger lattice. So each parton can fully occupy a band. So we don't want, ultimately we don't want any gapless fermion excitations floating around. We don't want any Fermi surfaces, and you certainly not get the phases you want. So we just going to assume that the bands are either fully filled or fully empty. Okay, so we take the F1 parton, and we're going to put it in a band which has Chern number -1. Now this should immediately set off alarm bells if you're awake, because I took this system and I assumed that this Tij was real because I'm assuming time reversal symmetry. And if Tij is real and you have time reversal symmetry, then there's no possibility of Chern numbers. To get Chern numbers, you have to break time reversal. You have to make Tij complex. You have to have some magnetic field which gives you phase factors as you hop around. Otherwise, how are you going to get a Chern number? So we just assume that the relevant mean field does break time reversal. So this is already dangerous. You have a system which has perfect time reversal symmetry, and you're trying to describe by a mean field theory, which breaks time reversal. Okay, that's worrying. But what we'll see is that in the end, when we go to the low energy limit, this time reversal symmetry is not important. It doesn't affect the universal aspects of the theory. Okay, and this, all right. So this subtlety of time reversal and exactly how this works out was only understood in recent years, especially with all the technology of SPT phases, where people have understood these things very carefully. I'm not going to explain those subtleties today, of course, because I don't really understand them myself. Okay, so modulo that dangerous thing. So what we're going to say is that the F1 fermion is always in a Chern number -1. So we just put it in some deep band and we forget about it. All we know that it has Chern number -1. But it could have some effects on the edges, and we'll of course have to bring them back to bear. And then for the F fermion, we have to have a phase transition. So we're going to also put it in some band, but we're going to have it undergo phase transition. And what phase transition will it undergo? It'll go phase transition which changes its Chern number. So there's one phase in which the Chern number of fermion Fc is 1, and another phase is 0. So that's our phase transition. And how does Chern number change? Well, you've seen this several times, but I'll show you again. If you have some band and another band, the way the Chern numbers change is that some 2 points in the band meet, and there's a Dirac point. So the bands kiss and move apart, and then when they move apart, the Chern number has flipped. So everything becomes a property of that Dirac point. So the vicinity of the critical point is only that Dirac fermion. And that's how, and what we're going to see is that phase transition of a Dirac fermion reproduces the superfluid insulator transition. Okay, so we take some Tij, and now we just have to manufacture Tij. None of the other details will matter, so that it actually has a Chern number changing transition. So I have given you an explicit Hamiltonian now. So this is the Hamiltonian I take. We have also, I think we've seen this when we did the, what was that? The chiral spin liquid, except we didn't have an epsilon naught then. Epsilon naught was 0 for the chiral spin liquid. So we have some nearest neighbor hopping T1 with flux pi/2 for every triangle. And just we're going to vary the value of epsilon naught. Okay, so you take this particular hopping Hamiltonian, here's it in momentum space, you diagonalize it, and this is the band that you get. Okay, so this I'm showing this exactly at the point where there's a Dirac node right there, and there's a mirror image band that's filled. This is the empty band. I'm not showing the filled band, the so-called conduction and valence bands. So there's the conduction band, there's a valence band, which is full down there. And here's our Dirac point. And you can do your computations and what you will find is that when epsilon naught is very large, I mean, you can kind of see when epsilon naught is infinity, then the bands are just totally localized. The particle either sitting here or there. The valence band is here, the conduction band is there. That's got to be topologically trivial. So when epsilon naught is very large, the Chern numbers of 2 bands are 0 and 0. And as you decrease epsilon naught, what happens is that they meet at this one point, and then they move apart. And when they move apart, the Chern numbers become 1 and -1. So at large epsilon naught, they have to be trivial. And so that tells you without any computations which way the Chern number has to go. So we're now interested in the vicinity of this Dirac point. And So now we have a quantum phase transition between two phases. The first phase has the F1 band is churn number -1, the F band is churn number 1, and the other phase is churn number -1 still, and this one is churn number 0. And we're going to see that these two phases are in fact the insulator and the superfluid. Okay, so let's right. So let's show this. So let's not even look at the transition. Let's look at the phases. So we start with the state C equals 0, C equals -1, C1 equals -1. That's actually a trivial insulator. Well, 1 minus 1 is a superfluid. That's kind of remarkable how that works out. All right, so the way we're going to show this is, basically turning exactly the same crank that we turned to get to establish the fractional quantum Hall state. We did the Parton construction of the fractional quantum Hall state. We introduced some gauge fields. We put all the fermions in Landau levels. Landau levels are nothing but churn bands. So we're doing almost exactly the same thing here. Churn bands are a little more powerful because you can actually have these direct transitions between them, whereas Landau levels are Landau levels. They're always in some churn number state. So you write everything in terms of these Landau levels and gauge fields, and you integrate out all the fermions in the gapped states, and you look at the effective low energy theory. In the bulk, you're going to get some Chern-Simons gauge theory, and on the edge, you're going to get some theory of edge states. And you really have to do both calculations. What's the bulk theory and what's the edge theory? And let's make sure that both of them come out to be what you would expect from the original boson picture here. So now we have a gauge invariance the moment we introduce this decomposition. So the moment we have this, now the theory is invariant under F goes to F times e to the I alpha, and F1 goes to F1 times e to the minus I alpha. And so there's a gauge field, which I think I'm calling B mu, and B mu under a gauge transformation goes to B mu minus D mu alpha. So the moment you do a parton decomposition, you allow for a U1 gauge field, and the two partons in this case have opposite charges under this gauge field. That's really all you need to know. And then you need to know the Chern numbers of these bands, okay? So now let's also couple in an external gauge field mu, just like this is the same gauge field that we coupled into the boson over here. So we couple a gauge field mu to the boson. So that external gauge field is acting on the boson. And now on the right-hand side, it can either act on F1 or F. We have a choice. In fact, the answer won't depend on whether we put the charge here or there. And I forgot what choice I made. So we just make one choice. Yes, and I took the external gauge field and put its charge on the F1. And the internal gauge field, of course, has opposite charges between F and -1. So these are our gauge charges. And then I could also make a table here of Chern numbers. And that's really all the information I need to say something about the low energy theory. Okay, so let's first look at the bulk theory. Yeah, okay. And then it's all done together. So yeah, so imagine that, so here there's another table. You can F and F1, and then you have Chern numbers. And right now the Chern number is C and C1. Just call it general C and C1. Okay. Then what happens when you integrate out the fermions? Well, for the fermion F1, it has Chern number C1, and it couples to mu. So you'll get a Chern-Simons term. Well, what am I doing here? let's start with F first. So F couples only to B mu, sorry. And it has Chern number C. So when I integrate out F, I'll get a Chern-Simons term for B, whose coefficient will be C, the Chern number for for F. Now F1 couples to both B and A with opposite sign. So it's coupled to A minus B or B minus A, and it's Chern number C1. So you get a Chern-Simons term for B minus A with Chern number C1. Okay, so that's the bulk theory in equation 8. And now let's take two different values. Okay, so let's take the phase where Chern number is 0, C is 0, and C1 is 1. Okay, so if C is 0, then this term is gone, and C1 is 1. And now I can do the integral over B mu. So when I do the integral over B mu, basically A mu disappears from the problem. You don't get anything out of it. There's no dependence on A mu at all because you can just shift it away. So this tells you that the final effective action in the bulk doesn't depend on A mu at all, at least in this low energy approximation. And that's what you expect in an insulator. In an insulator, you can put a magnetic field and nothing happens at all. But in a superfluid, if you put a magnetic field, you've got to have the Meissner effect. It costs you a huge amount of energy to insert a magnetic field in a superconductor or a superfluid. So that tells you, okay, at least this part is consistent. There is, there's no dependence on mu. So there's also no Hall conductivity because you don't have a Chern-Simons term after you do the integral over B in capital A. So it's not a Hall insulator, it's just a trivial insulator. Okay, so that's good. But this is not sufficient, strictly speaking, in this game, because so we have shown that there is no Hall conductivity, but we also have to show there's no thermal Hall conductivity, or in very fancy terms, there's no gravitational anomaly. But in pedestrian terms, which is the only terms I think in, we have to show there are no edge states. So we have to just turn the same crank and verify there are no edge states when the Chern numbers have this value. So naively, you would think, oh, there is an edge state. The F1 band has Chern number -1. So there should be an edge state associated of the F1 fermion. How come I don't have an edge state? Okay, well, the answer is the following. So the F1 band has a Chern number -1. So from the technology we have learned, there's an edge state. There's a chiral boson on the edge with coefficient -1, which describes the edge. Okay. Right. Okay. Right. But there's an important difference. This F1 band is not just coupled to nothing. It's coupled to this gauge field. We have to remember the gauge field. So there is a bulk gauge field, which is of course imposing the constraint that the fermions have to have this equal density and equal currents, because they're both at the same point as the original boson. So it's coupled to a gauge field, and the gauge field is B mu, and we also know how a gauge field couples to the edge theory. You take your so the F1 band couples to B mu minus A mu. So then you have a coupling between B mu minus A mu and the boson current. The boson density and the current. This is the edge state will couple to the gauge field. Okay, and now we have to do the integral over B mu. So that's the key thing here. We have to integrate over B mu to fully understand the theory. It's not a weakly coupled theory at all. When you do the integral over B mu, that's very simple. It just gives you a delta function of B mu phi, which tells you phi is constant, and bingo, there's no edge state. phi1, sorry, is not allowed to fluctuate because the gauge field gets rid of it. Okay, so that's the beauty of it. Here you had this thing seemed to have an edge state, but the edge state is pure gauge. It just disappears once you do the integral of the gauge field. So there is no edge state. So, all right, so I think we have satisfied ourselves, at least as far as the long distance properties are concerned. This phase with these Chern numbers is just a boring phase. It has no Hall conductivity, it has no superconductivity, it has no edge states. So, well, it's a pretty good candidate for being a trivial Mott insulator. Okay, so there, at least so far, everything looks good. So now let's go to the other phase where I have Chern number 1 and -1. This is a little more interesting, a little more complicated. And so now we have to see, is this a superfluid? Okay. So now C is 1 and -1. So I have to take this theory for the bulk and put C equals 1 and -1. And then when you expand it out, the term that's out of B squared will cancel out. Okay. So now I have the following theory. So I have a net Chern-Simons term left over for the gauge field, but I have this term here, which is B times A. So now I do the integral over B. And what does that tell me? Well, the answer depends on the flux. So the integral gives me a delta function. It tells me a delta function of the electromagnetic field. Well, that's just another word for the Meissner effect. You know, that the magnetic field has to be 0. Otherwise, you know, the partition, you know, otherwise the partition function is just 0. So you just get a delta function external field. That's the very simple answer. Now, of course, that's not exactly the answer. To get a proper answer, you have to put in high energy effects. So you put in the Maxwell term and you go through the same calculation with the Maxwell term. So you add another term, you know, like d mu b nu minus d nu b mu whole squared with a 1 over e squared out front. And you just, and then do the integral over B. Then it's more complicated. You have to do some Gaussian integrals. And what you'll get at the end is a term like this, which is a mass term for the gauge boson. And that's exactly the Meissner effect, if you go back early in the course. So in fact, the bulk, as far as the bulk is concerned, it looks like a superfluid. It just expels the magnetic field. All right, so that's looking promising. And finally, what about the edge states? Now we have, you know, it seems like things could blow up in our face. I have now not just one edge state to get rid of. I have 2 edge states, an edge state for the first band and an edge state for the second band. So I have 2 chiral bosons, one with Chern number +1, one with Chern number -1. And then based on these gate charges here, I also have to couple these chiral bosons to the gauge fields. So based on this 1, -1, and 1, I will get these terms. So B mu couples to D mu phi, that's D mu phi 1, and A mu couples to phi 1. Okay. All right, so now what happens? Well, when I do the integral over B mu, this tells me phi equals phi 1. So basically it sets phi equal to phi 1. So there are 2 counterpropagating edge states, but when they couple to the gauge field, the 2 counterpropagating currents have to be exactly equal, not just on the average, but dynamically. So you get a delta function between this and this. And once that's the case, this term will cancel that term. There is no edge theory left. I mean, the action, the Lagrangian is just 0 for the phi's. If you do the integral over phi, it'll tell you that the external field has to have 0 flux, which is of course, exactly what we wanted. That's the superfluid. So amazingly, it's a superfluid. So basically, you now find that if I take two bands with opposite Chern number, so this is not something you do in the fractional quantum Hall of. If you want to think of it in terms of Landau levels, you take, what we're doing is we take a boson and I split it into two fermions, and then I applied up magnetic field on the first fermion and a down magnetic field on the other fermion, and then put them in Landau levels with equal and opposite magnetic fields. So there's no net field. You don't really break time reversal either at low energies. And this thing is another way of describing a superfluid. And the superfluidity comes, right here. It comes from the fact that there's an internal gauge field whose Chern, whose self-Chern-Simons term all cancel out, and then this imposes a constraint that the external gauge field has zero flux. Okay, so any questions? So what we've shown, we haven't done any critical properties. We've just shown that these two phases, the first phase with C equals 0 and C equals -1 has the same basic properties as the boson insulator, the trivial insulator. And the other phase with C equals 1 and -1 has the same properties as a superfluid. And now what we want to do is go to the transition between them. We already know how to describe the transition between them in bosons. We give it the 5-fold field theory. What do we get here? So we're going to get some theory of Dirac fermions. Okay, so now what's going to happen is that, we have the F1 band, which has got this Chern number of -1. And it's sitting there. We've already taken care of the edge states, so we don't expect any fancy stuff with edge states at all. And so that other band will just sit there and give you some extra Chern-Simons contribution. We can just integrate it out. We can integrate out F1 as we have in this discussion here. But for the F band, right near the boundary, we can't integrate it out anymore, because then the F band will have this massless Dirac cone. So now it has zero energy excitations in the F band, and we just got to focus and zoom in on that band to get the critical theory. Now we have to keep the F band alive, but we can integrate out the F1 band, because that's some Chern band sitting somewhere else, which has a huge band gap that doesn't go to zero across the critical point. Okay. So what do we do? Well, we just take F1 band in this vicinity and write down a theory for it. Okay, so you just take the low energy limit of this, so this is all spelled out, and the kind of thing that I think you've done at least in the section. You start with this Hamiltonian, you write it in the low energy limit near the Dirac point, and then you introduce some Pauli matrix notation, which just gives you various, so this is what it looks like in this 2x2 Pauli matrices on the A and B sublattice space. And then you introduce the fancy bar notation and the gamma mu notation from particle physics, and there you get a Dirac fermion. So the free theory is the Dirac fermion at some mass m. And as the mass m goes to 0 and changes sign, you have your quantum phase transition. Okay, so that's what the F band does on its own. We can't integrate it out. It just becomes a Dirac fermion in some mass m. Now we have to couple everything to the gauge fields and ask what else is there. All right, so here, let's see. I haven't. Yeah, okay. Let's not worry about the external gauge field. You can put it back in later. So that's in this discussion here. I haven't worried about capital A mu. So the F1 band. Sorry, the F band gives you this, it couples to the gauge field with a certain charge, B mu. So just by gauge invariance, you know it has to couple to the Dirac fermion also in this minimal manner, d mu minus I B mu. Okay. Then what do I say here? Okay. Oh, no, I'm, yeah, sorry. I haven't made any approximation. I'm still keeping the A mu gauge field alive. So I'm looking only at the F fermion. And the F fermion doesn't even couple to A mu. I think that's why I chose to couple A mu to the F1, just to make my life simple as far as the Dirac fermion is concerned. The Dirac fermion only couples to B mu. Okay. So now, however, there comes a very important subtlety, which and some of my statements so far are actually not quite right. So what I've said is that as far as the F band is concerned, I can just zoom in to the vicinity of the Dirac node and just take some low energy theory for the F band near the Dirac node. That's not quite right. And one way you can see that's not right is to compute the Chern number of the band. So here's some low energy Hamiltonian. Okay, if you don't like it this form, here's the Hamiltonian. You just take this Hamiltonian and you compute its Chern number. Take this Hamiltonian, let Qx and Qy run from minus infinity to infinity. So just think of this as the Dirac cone going forever in momentum space, rather than being part of this band. So just take a Dirac cone and imagine that's your dispersion and just compute the Chern number. And what you'll find is that the Chern number is actually not an integer. You'll find from a Dirac cone, when the sign of the mass m has one sign, it's its Chern number plus a half, and when the sign m has the opposite sign, it has Chern number minus a half. So this is just a property of a Dirac single Dirac cone. It doesn't have an integral Chern number. And this is intimately related to what people call the parity anomaly and why you always have to have even number of Dirac fermions in any band structure, because Chern number has to be an integer, whereas a single Dirac cone has a Chern number either plus a half or minus a half. So, however, we know that our band, the F fermions, has an integer Chern number. I mean, it has to. It's just a perfectly self-respectable band on the square lattice. So what about the other half? So how come I'm getting another half? Well, the point is that there is, as you can see in this picture, another Dirac cone. That's some way to think about it. And that Dirac cone is also going to give you a half integral contribution. So the two Chern numbers we had was 0 and 1, right? So what we expect is that this one either gives you plus a half or minus a half, and the other one always gives you plus a half, because that doesn't close. It just has one sign of the mass, which could be large, but always gives you plus a half from there. So your Chern number either is half plus a half, which is 1, for one sign of the little mass m, or it's minus a half, which gives you 0. So the bottom line is I do have to worry about this 1/2 contribution from the other Dirac node, even though it has a gap, which could be really large. And in fact, even that's an approximation, because the actual band is neither a Dirac cone, either massless or massive. I've shown you the band, and it's really the integer comes when I actually integrate over the whole thing with this particular band structure. But we say, okay, in the low energy limit, let's just imagine that this Dirac cone goes all the way to infinity, and just put in a half from the rest of the band to make everything integral. Okay, so that's the condensed matter fudge. You say we're going to put in a half, but if you run into trouble, just remember you have to go back to the lattice. So we add another term, another half Chern-Simons term from the other Dirac cone, which is massive, of the F band. So, all right, now if I'm a particle theorist, then you start having a heart attack at this point, because you say, what do you mean by Chern-Simons term with a half integer? That theory is not even defined. You know, go back to our chapter on Chern-Simons theory. The Chern number was always the coefficient of the Chern-Simons term was always an integer. The theory didn't even make sense when it wasn't. That's completely correct. But what I mean by adding this half a term is I just have to just keep in the back of my mind that I only evaluate this upon including the other half from the psi fermion, so that it's always an integer, either 0 or 1, depending on the sign of m. So that's just something I have to remember. Now, if I was a particle theorist, that this is not, don't want to ever refer to a lattice. So there's another way to account for all this. Let me put this down here. Something called the eta invariant. Yeah, here it is. So they have a fancy way of doing this. They represent this whole stuff by the eta invariant, which is actually truly gauge invariant. And it has deep connections to the Singer theorem and all this beautiful stuff that I can't say I understand. But anyway, but in practice, this is good enough for us. All right, so we just keep this one half integral Chern-Simons term, or just remembering that actually there's never going to be a problem because the half will always cancel with this other half. Right, and there's in the theory of topological insulators also, you get a half at the edge, and that's an anomaly, and there's a bulk contribution that makes sure that everything works out right. Okay. All right, so now the theory, low energy theory of the F band is right here with this half Chern-Simons term, and as m goes through 0, then you have this phase transition between a superfluid and an insulator. And then now all I have to do the contribution of the -1 band of the F1 band, and that's no problem. I can just integrate it out. It couples to B minus A, and you add that up and you expand everything together. So basically, I just take this contribution with C1 equals -1. Where is it? Yeah, I just take this term and I add it to the theory of the Dirac fermion with this half quantized Chern-Simons term, and that's it. So now I have this theory. So this is, yeah, so if I ignore the gauge field, the external gauge field, it's a Dirac fermion with mass m with Chern-Simons level a half. So it's, sometimes people say it's U1 level a half. This is the notation you might see. So you have the fermionic theory psi coupled to, it's a fermion psi coupled, Dirac fermion coupled to U1 level a half. So the claim is that this thing is dual to a Wilson-Fisher boson phi. So that's the duality that we have established. Massless, nearly massless Dirac fermion at Chern-Simons level a half is in fact our favorite XY critical point between a superfluid and an insulator. That's the claim. And this theory, okay, there's very detailed discussion of this in, I think, maybe Witten's RMP article. It's in fact time reversal invariant, suitably defined when you properly use the eta invariant and all of that. So all is fine. Okay. Right, what else do I have said here? Oh, yeah, I don't know. You can ask now, what about the operator correspondence? So yeah, that's a little subtle, and I certainly don't have time to go into it. So for the Dasgupta-Halpern duality, the boson on one side was the monopole on the other side. And similarly here, in fact, it's almost exactly the same thing. The boson in one theory is the monopole in this theory. Yeah, okay. Yeah, so the monopole, and there's some subtleties with fermion zero modes that you have to take into account, but it turns out that the boson is the monopole operator in this Dirac fermion theory at Chern-Simons level I have. Any questions?
Or is it the monopole plus the fermion disruptor?
Yeah, okay, there's a discussion of it. Right, so the boson is F times F1. And then you notice that the F1 has a Chern-Simons Chern number -1, so that monopole is precisely an F1 particle. But then that monopole has a zero mode, and you have to occupy the zero mode on it to make sure this works out. And and the monopole also has to be a boson. Okay, so I won't go into this. There's a nice article by Karch and Tong which discusses this, not in precisely this language, but anyway. So these monopoles, it turns out, have zero modes, somewhat analogous to the zero modes of visons in the non-abelian Kitaev phase that we talked about. But now these are monopoles, and they don't have Majorana fermion, they have complex fermion modes, so it's a little simpler. You don't get any non-abelian statistics or anything like that. What you get are just bosons turning into fermions or vice versa. All right, in the remaining 2 minutes or 5 minutes, let me mention Fermion-fermion duality, which has seen a lot of discussion these days, especially as theories of the nu equals 1/2 quantum Hall state, and whether using composite fermion and the composite Fermion-Fermi surface, there's been quite a lot of progress and many papers written on it, and also a lot of debate what this Fermion-fermion duality actually means. And I tried to do a lot of them, and it's extremely complicated, but I just want, I think I have a presentation here, which is, I think, is extremely simple, which gives the basic result using all the tricks we've developed in this course. So I just can't resist mentioning it. So let me just make the basic claim. Okay, so far what we've done, we described a bosonic transition between a boson and a superfluid and an insulator. So now let's describe another transition, which is fermionic, which is exactly the transition I described before for the F fermion, but use it in terms of the electron. Suppose I have an electron which undergoes a phase transition, an integer quantum Hall phase transition, where its Chern number changes from 0 to 1. So this is just free electrons with the Chern number changing transition. And we know what that's described by. I just showed you it's described by a Dirac fermion. So you have just a free Dirac fermion in some mass m coupled to some external gauge field. And you have to add the extra 1/2 to make sure the whole thing is gauge invariant. All right, so that's our phase transition. So that takes the place of the superfluid insulator transition. You have just an integer quantum Hall transition. But what we try to do is to describe this integer quantum Hall transition by the Parton method. So now I have to take my original fermion and write it as a product of 3 fermions, which is what we did for the Laughlin states in the Jane sequence also. And then I'm going to put these fermions in different Chern bands. So there's 3 Chern numbers to keep track of. And it turns out that the 2 phases correspond to 0, 1, 1 and -1, 1, 1. And you just take the low energy limit in exactly the same way I just did it. And when the dust settles, you get a Fermion-fermion duality, which in fact, in the absence of external gauge field, there is no Chern-Simons term on either side. So basically what you end up showing is that this theory, fermion coupled to U1 gauge field, Dirac fermion coupled to U1 gauge field, is the same as the dual of a free Dirac fermion. there are some subtleties with fractionally quantized Chern-Simons term that you have to be extremely careful about. And there's a long article by Sinthal and Witten and others about that. But which is also, I mean, I claim that my treatment here gets all of those right too, all those subtleties right too. But I don't have time to go into it. But you can read all about it. But that's the main result that's worth mentioning, that this theory here, Dirac fermion coupled to some emergent gauge field A mu, is the same as a Dirac fermion not coupled to any gauge field. In fact, you know, this seems to have a very the parallel with the Das-Gupta-Halpern duality is also quite striking. The Das-Gupta-Halpern duality had a boson on its own, 5-foot field theory. It was dual to a boson coupled U1 gauge field. Amazingly, with a lot of subtleties, a similar statement is also valid for Dirac fermions. And there's not a proof, but a very strong argument for it in these notes. All right, I'll stop there. The chat message, thank you. Okay. All right. Questions? Okay, so I've given you hopefully a lot of food for thought. There's much more on these notes than I've had chance to go through, especially the last 4 chapters. There's another chapter on application of this to spin liquids. Well, you know, there, of course, you're coming to things that are very much current research problems of interest to me and many other people. Yeah, you know, this is the basic tool on everything we learned today. How just by having a Dirac fermion change its mass, we can get all kinds of interesting descriptions of quantum critical points, including the very first quantum critical point we met, which was the boson superfluid insulated transition. Questions?
Yeah, I have a question on the C equals 1, C equals C1 equals -1 cancellation that we did.
Yes, yes.
Is the interpretation that we do have the edge states, but they have opposite charges and basically that cancels each other out? Or I guess I'm confused because the F1s would still have a charge relative to the external gauge field. So if there was any current of the F1 edge state, that would still carry the actual charge with respect to the external gauge field.
Yeah, so the claim is that there could be something happening at the edge, but it's not gapless. So the logic is here, first of all, you do the integral over B mu, which that's always something you have to do completely. And that makes sure that these two terms exactly cancel each other out. And if you put in higher order terms, you'll find that means that there's no gapless boson mode. But in the limit, we only keep these terms around and not the velocity terms. So you can throw these terms out. Then when you do the integral over phi1, you know, you said there's still some phi1 field left over. Yes, it's true. But in this approximation, if I do the integral over phi1, all I get is a delta function of the external flux. So that tells me that's exactly what I wanted. Even the edge doesn't want any magnetic fields around, just throws it out, it expels it. Now, there are many higher order terms that you have to put in and make sure that this all is consistent. I haven't done that. I can't say I've actually ever done it, but I feel pretty confident when you do that. You'll find things like A squared terms, various places, which you're happy to live with. And you may get some gap modes, but you will not have any gapless modes. Yeah.
I see. And also just a logistical question. I missed Monday's lecture, but I don't see it yet on the recordings. Did you get a chance to record it or not?
It was recorded. Sorry, I may have just forgotten to let me just look at it right now. Oh yes. I just put it on there right. It's there now. Sorry, I just forgot to hit the publish button on the Zoom website, which I just did hit. So you should see it now.
I do, yeah.
Okay.
Thank
great.
you. Thank you very much.
Sure. In any case, if you go to the pages file, it's a bit late now, but under the pages file, there's a link. There's a file called Zoom recordings. It's there. It's always been there too. Oh, okay. But yes, so I forgot to hit the publish button. Thank you. Anyway, you can see it now, right? What I did forget to record was the discussion session yesterday. Sorry about that. But I gather you went through over similar material in a section, and I added some, gave my scribbles on Slack. Mainly, we discussed problem 4C in the homework in the discussion session yesterday. Okay, well, we'll have another discussion session tomorrow. And then the first, the schedule is rather light for the next week. I think in terms of your presentations, the next upcoming meeting is, here we go, 2:45 p.m. on Friday, presentation by Yun Chao, and then 4:15 by Zhengyan Shi. Everyone has accumulated towards the end. Okay, we'll have a very busy time in 2 weeks, but next week is rather light. All right. Okay, so see you tomorrow and in the presentations, I hope. Thanks a lot.
Thank you.
Thank you.
Thanks.